In this video, we're working some surface area questions in multivariable calculus. So the first one is find the area of the portion of the plane x plus y plus z equals 3 that sits over the first quadrant. And I could have said that sits in the first octant or over the first quadrant. I think over the first quadrant is kind of more consistent with the language I'm going to be using later on. Okay, I think I need to remind you that the formula for surface area is equal to the double integral over some region the square root of 1 plus fx squared plus fy squared dA. So what I'm going to say that sits over the first octant, well, I'm going to need to solve for z. Z equals 3 minus x minus y. Okay, so if, I'm thinking about the first octant, that's where x and y and z are all positive. So if, I look at well, I guess that sits over the first octant, and it's going to be a plane that intersects the xy plane somewhere, and that would be where z equals 0. So I'm going to say 3 equals 3 minus x minus y, and so this would be x plus y equals 3. And I know that in the xy world, the picture of this is, I'm trying to think how to explain that, but this is the picture that we're looking at. Okay, that's where it cuts through the xy plane. Okay. And then, it's going to do something else over it, but we just deal with that with the partial derivatives. So, as far as the region that we're interested in, I would say it might be easier to talk about y first. So, from the bottom to top, okay, y is in the interval. Okay, bottom looks like y equals 0. The top looks like y equals 3 minus x. Meanwhile, x is running from 0 up to 3. So those will be my bounds of integration. Okay, I will need to take fx and fy, okay, but that's my formula right there. That's like f of x and y. Okay, so fx is going to be -1, and fy is also going to equal -1. So my double integral is going to be pretty easy to compute. Integral from 0 to 3, integral from 0 to 3 minus x of the square root of 1 plus 1 plus 1 is square root of 3 dA. All right, and if I factor out the square root of 3, I'm going to employ a little trick here. The double integral of this region with respect to area, well, that's just going to be the area of the region. And I know how to find, that's, square root of 3 times the area of this triangle that has width 3 and height 3. So that's 1/2 times base times height. So it's going to be 9 root 3 over 2. And, if you want to take antiderivatives and do that, be my guest. But, I think I'll just go ahead and do it the faster way. Set up but do not evaluate a double integral gives the area of the surface of the graph over region R. Okay, this is going to be like, yeah, this one's great because x is just between 0 and 2, y is between 0 and 8. So I'm going to say, okay, just kind of either way I want because it's just got to be set up, right? 1 plus, we're going to need fx. Well, e to the thing is its own derivative. And then the derivative of 3xy with respect to x, well, that would be 3y. Okay, so if I square fx, I'd have 3y squared. I just have 2 copies of both of these, so I'd have 9y squared. E to the 3xy times e to the 3xy would be e to the 3xy plus 3xy is 6xy. Okay, and we're thinking about squaring that, multiplying the exponent by 2 either way. Fy is going to be very similar, e to the 3xy multiplied by 3x for the chain rule. And if I square that, I'm going to have 9x squared e to the 6xy. Okay, and then I'm going to have in here 1 plus 9y squared e to the 6xy plus 9x squared e to the 6xy, because we don't have to evaluate this. We're not going to simplify or factor anything. Y was running from 0 to 8, so it would be dy and then dx, and that would be a set up and not evaluated integral that represents the surface area. Number 3 asks for the area of the portion of the surface here that lies above the plane z equals 7. So pretty much what I'm going to have is like a paraboloid that kind of goes down, and then that's going to intersect with this plane, which I guess really I kind of want that to be invisible, so I'm going to just do it about like that. I'm just going to forgive the imperfection there, and then, but I should probably draw the intersection right back there. It's going to be, some kind of circle or oval or thing, but the plane z equals 7, and, probably shouldn't be able to see part of this. Let me erase something. It's a little bit more like it. That's generally what's going on there. So I'm going to find the equation of that intersection by just going ahead and setting these two things equal to each other. 16 minus x squared minus y squared equals 7. And so that's going to be where 9 equals x squared plus y squared. Okay, this is a circle centered around the origin with radius 3. We're going to want to use polar coordinates and say r is between 0 and 3. And theta is between 0 and 2 pi. That will make our lives much, much easier. Okay, now I'm going to need partial derivatives. So zx equals negative 2x, which, because we're going into polar coordinates, is negative 2r cosine theta. Okay, if I square zx, I'm going to get positive 4r squared cosine squared theta. Zy is going to equal negative 2y, which would be negative 2r sine theta. And then if I square that, a very similar thing is going to happen. So 4r squared sine squared theta. And if I add these together, okay, I have zx squared plus zy squared. If I factor out the 4r squareds, I'd be left with a cosine squared theta plus sine squared theta, which we need to know is equal to 1, so that's equal to 4r squared. Okay, so that will be something that we'll need to be ready to work with when we set up our integral. Okay, so it's going to be a double integral over some region. Now, we usually do r d theta, so that would be 0, 3, 0, 2 pi. Okay, and then there's going to be a square root of 1 plus zx squared plus zy squared, so that's 1 plus 4r squared. And then dA is r dr d theta. It's like, oh, this is perfect. Because what I could do, if you wanted to use technology on this, you could run the integral from 0 to 3 of 1 plus 4r squared times r dr, right? Just ignore the outside and then multiply by 2 pi because it doesn't have any theta in it. Or we could use u substitution, and that's what I'm going to do. I'm just going to zoom in on this integral and solve it using u du. All right, so I would prefer for this to be an 8r instead of a 1r. Okay, so I'm going to make it an 8r, and I'm going to account for that by dividing by 8. So now u equals 1 plus 4r squared. du is 8r dr, which happens to be exactly what I've got. And then, okay, I need to convert the bounds. When r equals 0, that's going to give me u equals 1. And when r equals 3, that's going to give me u equals 4 times 9 is 36, and 1 is 37. That's weird. Okay, I do kind of remember getting this. I think somebody requested this in class. Okay, so this is going to be 1/8 of the integral from 0 to 2 pi of the integral from 1 to 37 of the square root of u du. And that's going to be 1/8 of the integral from 0 to 2 pi of 2/3 of 37. Oh, no, it's not like that. 37 to the 3 halves minus 1 to the 3 halves. D theta, it's supposed to be a 2 pi, 27. I think I got carried away with 37. Yeah, and so then I'm just going to get 1/8 times 2/3 times this monstrosity times 2 pi, because I'm just integrating a number d theta from theta equals 0 to theta equals 2 pi, and there I'm going to have an exact value for the surface area, and that was, there we go, we got it. Okay, find the surface area for the portion of the surface z equals xy that's inside the cylinder x squared plus y squared equals 1. Okay, this is going to be another one that we want to do polar coordinates. If it's inside that cylinder, that means r is going to be less than or equal to 1 while greater than or equal to 0, and theta will run all the way from 0 to 2 pi. Okay. Surface z equals xy, I'll take my partial zx equals y and zy equals x. So if I change that to polar, which I know is going to happen because then I've got a cylinder, a circular type thing, cosine theta, yep. And so if I square zx, that's going to be r squared sine squared theta. Zy squared is r squared cosine squared theta. So if I added them together, it's going to be r squared times something that's equivalent to 1 for every theta. So that's just going to be r squared. Okay, now we're going to be double integrating. Let's see, I don't need that quite yet. Theta going 0 to 2 pi, r going 0 to 1. The square root of 1 plus r squared, okay, because it's 1 plus zx squared plus zy squared. dA is r dr d theta. Okay, then go in here. I'm just going to do the exact same thing as before. I'm going to do u substitution. I'm going to let u equal 1 plus r squared. Okay, well, I would prefer this to be 2r, so I can make that happen that way. So du equals 2r dr. And then that's exactly what I've got. Okay, I'm going to convert my bounds. R equals 0 gives me u equals 1, and r equals 1 is going to give me u equals 2. So I'm going to have a 1/2 of the integral from 0 to 2 pi. In u, I've got the integral from 1 to 2 of the square root of u du d theta. Right, so 1/2 of the integral from 0 to 2 pi of 2/3 of 2 to the 3 halves minus 1 to the 3 halves d theta. This is going to play out just like the last one. And so I'm going to have 1/2 times 2/3 times 2 to the 2/3 minus 1 times 2 pi, and that will be my surface area. So my area of the portion of the surface that sits inside that cylinder. And I think that's the one that looks like a Pringle if you graph it on Desmos. The last two, I think, right? Nope, there's 4 more. All right, area of the surface here that sits over the region defined by x squared plus y squared less than or equal to 4. Okay, we're going to be having this again, and I think I might start to like model the technology technique after I've done the first 4 by hand. Let me see if there's anything. Okay, I do like maybe the look of number 6, and maybe possibly by hand. Yeah, we'll see what happens. Number 5, I'm going to use some technology because this one's just so similar to the other ones. All right, I'm going to be switching this to r is less than or equal to 2, but positive, and theta is between 0 and 2 pi. I mean, it's going to be the exact same u substitution again, so I feel like we can do this a little better. So z equals 13 plus x squared minus y squared. Zx equals positive 2x, which is positive 2r cosine theta. And you're like, oh, well, this one's minus y squared. This one might work a little different. But when you go ahead and square these, they end up, you lose that negativity. So it's actually exactly the same. All right, so zx squared plus zy squared is going to be equal to, if I square these, I'm going to have a 4r squared on each of them, and then something left over that's equivalent to 1. So it's going to be 4r squared. I mean, even the same integrand. So the integral from 0 to 2 pi, integral from 0 to 2, square root of 1 plus 4r squared, r dr d theta. Okay. Now, yeah, so let's bring it in a calculator window. All right, that may have taken me longer to type in than it would have taken to just integrate, but okay, I've got this 5.757, and if I'm going to just get that number and throw that as the integral, or as the integrand of my integral from 0 to 2 pi d theta, okay, it's just going to be that multiplied by 2 pi. So I might go ahead and just multiply the 2 pi out here and get 36.177. Okay, and then that would be my answer right there. Okay, now this area of this surface that sits over the region where f is between 0 and 1. Well, let's just figure out what the region is where f is equal to 0. Let's see where this is going. Okay, f of x and y equals 0. That's where 0 equals the square root. And x squared plus y squared equals... Oh, no. If this was like 1 to 4, that would be a much more interesting question because then it would be over an annulus and, r would not just be 0 to something. But this is just going to be x squared plus y squared equals 0. Well, that can only happen at x and y equals 0. Okay, so that's at the origin. That's just the only point that makes that happen. Okay, f of x and y. And like f is always less than or equal to 1. So, or no, I mean, f is always greater than or equal to 0. That's definitely not true. It's always less than or equal to 1. Because you can make x squared and y squared as big as you want. So, f of x and y equals 1. 1 equals that square root. Okay, you square both sides. X squared plus y squared equals 1. And there we go. That's the unit circle. R is between 0 and 1. Theta is between 0 and 2 pi. These partials might be a little bit more annoying. Fx is going to equal 1/2 x squared plus y squared to the negative 1/2 times the derivative of the inside with respect to x would be 2x. And I know I'm going to need to convert these to polar because I've got these circular regions. I got these x squared plus y squareds. So really this is 1/2. The thing inside the parentheses is equivalent to r squared to the negative 1/2. We can figure that out. Times 2r cosine theta. Okay, so that just means r to the negative 1. Oh, and that's going to cancel off, and so is the 1/2 and the 2. That's really nice. So I'm going to just have a cosine theta. Oh, wonderful. Okay, fy equals 1/2 of that thing to the negative 1/2 times 2y for the chain rule. Okay, so that's going to give me 1/2 of r squared to the negative 1/2, which is going to be r to the negative 1, times 2r, which will just give me 1 now, times sine theta. 1 times sine theta, that's just going to be sine theta. Okay, and now I've got fx and fy, and if I square them and add them together, I'm going to get 1. So the double integral over region R of 1 plus fx squared plus fy squared dA. And I don't know if we would have been able to see this in rectangular. We probably would not have been able to see this in rectangular coordinates. If we convert this, this is going to be the double integral over that region that's like equivalent to the unit circle of the square root of 1 plus another 1 when we square cosine and sine. So that would be square root of 2 dA. But that's equal to root 2 times the double integral over r of dA, which is just the area of r. And this is a unit circle centered at the origin, so pi r squared, that's pi times 1. So this is pi times the square root of 2. Okay, and that's another situation in which just like looking at the double integral of dA as just the area of the region really does shine. Because we could have gone through lots of integration steps, and especially if we stayed in rectangular, that would have been just horrible. We could just think about the area of a circle. All right, now the last two, find the area of the surface defined by this function here that sits over the rectangle with vertices at the origin and these 3 points. Well, I'm going to need to draw that region because I can't quite visualize it. Okay, here's one vertex, 0, 4, a rectangle, 0, 4, 3, 4, 3, 0. Okay, so this is going to be my region. Oh boy. It's going to take a second to color in. There we go. All right, that's the region we're integrating over. Call that region R. Make it look really nice. So if I want my partial derivatives, I'm going to say zx equals 3/2 x to the 1/2, zy equals 0, because this thing doesn't depend on y at all. So zx squared plus zy squared is going to be, if I square 3/2, I'll get 9/4. Okay, we'll get an x there plus 0 squared, so that's just 9/4 x. Okay, well, we can work with that, I suppose. And then we're going to double integrate over region R. The square root of 1 plus zx squared plus zy squared is 9/4 of x. Okay, and dA. Now, we're going to have to anti-differentiate this. Right? There's not really any way around it, because 1 plus 9/4 x square rooted is not just a constant. So what I'm going to need to do is maybe say, all right, x is running from 0 to 3, and y is running from 0 to 4. So let's just knock out the antiderivative first, and then multiply a result by 4. That's what I'm thinking. Yeah, sure, why not? So the square root of 1, actually I'm going to write this to make it our anti-differentiation as easy as possible. Okay, and then 0 to 3 was x, and 0 to 4 was y. Okay, yeah, we need to think of an antiderivative for that with respect to x. Well, we can just think of one using the chain rule, right? Because it's linear on the inside. It's been a while since AP Calculus, and it's a very big theme in AP Calculus these days, these kind of chain rule antiderivatives. But I'm going to add 1 to the power, divide by the new power, so 2/3 of that. But I have to account for the chain rule as well. And so I need to divide by 9/4, or like multiply by 4/9. And let me just think about taking the derivative here with the chain rule, make sure it works. 3/2 kills off the 2/3. Times, leave that the same, reduce the power by 1, that's where we get 9/4 x plus 1 to the 1/2, and then we multiply by 9/4 for the chain rule. Yes, this is it. Okay, so from 0 to 3. Hey, we gotta be careful when we plug in 0, we're not gonna get 0 here. So this is 8/27. Let's see, I've got plenty of room. So 8/27. I'm just going to like leave that factored out. And then, because I'm going to have two different things of the 3/2 power subtracted from each other. All right, 9/4 of 3 is 27/4 plus 4/4 is 31/4. What on earth? I assumed we were using technology for this one. Minus 1 to the 3/2. It's going to be that. And then we're still integrating that from 0 to 4 with respect to y, but notice that is a constant, so that'll just end up multiplying by 4. 8 times 4 is 32/27. Like, it looked so promising, right? That 9/4 x was going to be a square number. Or no, it wasn't exactly. It was going to be 27. Okay, so I know it's just fool's gold. All right, 32/27 times 31/4 to the 3/2 power. Subtract 1. And that's going to be our exact value for that surface area. Okay. Okay, now we're going to find the area of the surface that sits over a triangle. I'm going to draw that one as well. Okay, vertices at 0, 0, x equals 2, y equals 0, and x equals 2, y equals 2. All right, so it's going to be going through that point and like that, and so guess, yeah, that's our triangle. I guess it's nice that it's a right triangle, but I don't think that's going to really be all that helpful for us. I'm going to draw some highlighter over it, make it look real nice, and say, all right, that's going to be my region. Okay, so we're going to have, okay, yeah, if we think about y is going to run from 0 up to y equals x. That's the line that goes through 0, 0, and 2, 2. So y runs from 0 up to x. Okay, y equals 0, y equals x. I'll even write that in there. I haven't done that enough this year. Okay, y equals 0, y equals x, and then x is starting at 0 and ending at 1. Okay. Then, after that, I need my partials. Gx equals 2, gy equals 2y. So gx squared plus gy squared equals 4 plus 4y squared. I'm going to be interested in taking the integral as x runs from 0 to 1 and as y runs from 0 up to x of the square root of 1 plus gx squared plus gy squared, that's 5 plus 4y squared. Okay, that's dy and then dx. Okay, this is not the type of integral that we are able to take by hand, right? Square root of 5 plus 4y squared, that doesn't have a closed form antiderivative. Okay, if we tried to use the chain rule, it would go awry. Okay, you would try to divide by something that was variable in y, and you would, if you checked with the derivative, you'd need to use the quotient rule, and it'd just get worse and worse and worse. All right, so what I'm going to do, I think, because this one... Oh, no, we're not. We're going to have to do the first step by hand. All right, because we've got a variable bound. Yeah, I like this one. All right, so we're going to reverse the order of integration. So we're going to go back over here. We're going to erase some stuff. So I'm going to get kind of, yeah, rid of almost everything. Right? Just like change my perspective on this. All right, so I've got this line here. And that was the line y equals x. Okay, so that means if I wrote it as x equals, it would be x equals y. Okay, so I have to think side to side first. If I'm thinking dx first and then dy. So from this perspective, on the left edge, I've got x equals y, and on the right edge, I've got x equals 1. And then for y, okay, y is starting at 0 and ending at 1. Okay, so y runs from 0 to 1 now. So now we're going to reverse the order of integration. I'm going to say, okay, when I switch it, it'll look like this, and x is between y and 1. Okay, I'll have the integral from 0 to 1 in y, and I might emphasize that, of the integral from x equals y up to x equals 1. Oh, but then this one's also kind of hopeless, so you need technology on this one anyway. So if you wanted to just go ahead and, I don't know, see if you had one that could do it symbolically. I don't know. I don't think Desmos will do that, and I kind of try to limit myself to that. Integrand didn't change by the reversing of the order of integration. 5 plus 4y squared dx and then dy. Okay, so that'll bring in a 1 minus y, right? Because it'll have an x on the outside of that square root. X will run from y to 1. I'll plug in 1, plug in y, and I could factor it out and just have 1 minus y times the square root of 5 plus 4y squared. And because 1 minus y is not proportional to the derivative of 5 plus 4y squared, I'm not going to be able to use the substitution on this. Hope you'll forgive me not like actually showing you the steps of me going to a calculator and typing this in. I'm just typing in the integral from 0 up to 1 of 1 minus y times the square root of 5 plus 4y squared dy, and I'm getting 1.188. 1188. Okay, and there you go. That's a good example of when we need to use technology. I'm not saying that it's impossible to compute that integral. That might be one that you could look up in like a table of integrals, or possibly use a trig substitution on. I really don't like that factor of 1 minus y on the outside for trig sub, though. But, you know, in our class, we'd be perfectly fine to use technology for that second layer of integral, because you had to do the first layer by hand, at least with the types of calculators we've gotten in people in my class. Okay, so that's number 8. That's all for this problem set. Thanks for watching.